If it is come here, it will be
It's all automatic. I don't know how it is coming here, not here.
okay. Anyways, it's on WebEx.
Yeah, WebEx people can see your screen.
Yeah. Okay, shall we start?
Yeah. Okay.
Hey guys, can you hear me on WebEx?
Yeah, we can hear you, Prashant.
Okay. Okay. So we'll get started. Today's topic is TI-LSA. So even though it's just TI-LSA, I'll be starting from the basic. I'll start from IP-FRR, then move to RLSA, and then finally go to TI-LSA. Because without doing IP-FRR and RLSA, you won't appreciate why TI-LSA is so good. So I thought I'll add both of them. And if I add them, it will be like a complete FRR section, including all options. So that way, it benefits overall. Okay, so first thing, what is the need for FRR, right? So there's a lot of research and a lot of work gone into FRR. Basically, what is the need? Assume we have a ring topology like this, and if you have doubts anywhere, feel free to stop me. So you have a ring topology like this. My source router is R1, as in that's where traffic is coming into. It's coming into R1, and then it needs to go out of R5 to 150.0.0.0. That is my destination prefix. The best path is from R1 to R5, right? Now, so this is a topo. Please keep in mind all link costs are 10. I'm running ISIS as the IGP, so by default the link cost is 10 everywhere. Okay, now exactly what I'm saying, that R1's best path to reach 150.0.0 here is directly to R5. Now what happens if R1 to R5 link goes down, fiber cut or whatever happens, right? Now what R1 needs to do is R1 needs to run SPF again. Now this link is down, it has to run an SPF again. It might take few 100 milliseconds or whatever. And then it has to figure out that my R1, R2 path is my best path now. But this takes 100 milliseconds or so. And then it has to generate that update, send it to R2. Now currently if you see in this diagram, right, R1's best path to reach 150.0.0.0 is R1 to R5. What about R2? R2's best path to reach 150.0.0.0 is through R1 itself. You see, right? Because the link cost is all 10. If you look at R3, R3's best path to reach 150.0.0.0 is through R4. So R3 is not going to use the failed link by default. R3 uses R4, but R2 will use the failed link. As soon as the link goes down, R2's routing table says I have to go to R1. So in that case, what R1 needs to do, R1 needs to first run SPF, and then it has to generate the update and send it to R2. R2 has to receive the update, run SPF again, and then point its routing table to R3. All of this may take a couple of 100 milliseconds, or depending on the number of prefixes. If your prefixes are very high, it can take a couple of seconds as well. right? So here I've mentioned typically hundreds of milliseconds, considering just a few hundred routes or so. The point is, when this happens, service glitch is observed. So when I say service glitch, you look at this video, okay? Now, if so in terms of low resolution and high resolution video, if the drop of traffic, say the worst case drop is say, I mean, consider 900 milliseconds or 700 milliseconds in case of high resolution traffic, you see how the video is. So all your WebEx calls and voice, I think you just hear a small glitch, but video there'll be a big impact. And other time-sensitive applications like trading, hospital networks, all of that, they will see a big impact, which is not acceptable to them. That's why this, right, this normal way of falling back is not good enough. That's why FRR came into being. So this is exactly what I explained, that if R1 to R5 link goes down and R1 converges in 100 milliseconds, that it has to go through R2, but R2 has not converged yet because R2 has to receive an update from R1. So what R2 would do, when once R1 sends traffic to R2, R2 will loop it back because R2 is not yet converged. So this is the issue. I mean, this is what I just explained. Now after sub-second, I mean few hundred milliseconds, R2 converges and then R1 can send traffic to R2. This is what the thing is. Local LSA, okay. Now assume the same network, but now the link cost is 100 here. Which means R1's best path to reach 150.0.0.0 is through R5. What about R2's best path? Through? R3. R3, right? So if as soon as R1 detects R1 R5 link is down, can it send traffic to R2 immediately as soon as it converges? It can, right? Because R2 is now not going to loop it back. So this is the principle of local LSA. So what R1 will do is R1 will run SPF on behalf of its directly connected neighbors. As in, R2 is a directly connected neighbor, so R1 will run SPF with R2 as root. Similarly, R1 will run SPF with R5 as root. In this case it won't because it's protecting R1, R5. So when R1 runs SPF with R2 as root, it figures out that R2's best path is not going back to R1. So R1 can safely send traffic to R2. This is the principle of local LSA. Directly connected neighbors, run SPF with them as the root and see if traffic is going to come back to me or not. If it is not going to come back to me, then you can send it. Yeah, this is exactly what I've explained in the text. This is the principle of loop-free alternate or LSA. Now, LSA selection rules, I mean, it's just theory. When I send the PPT, you can read it, but the principle is this. So, source router runs SPF with its directly connected neighbors as root, figures out if the directly connected neighbor will send the traffic back to me or not. And then the configuration for this is, whether it's ISIS or OSPF, the config is very similar. I've just mentioned ISIS config here. Is under the address families, just say fast reroute per prefix, that's all. There's a single line command under all the interfaces that you want protected.
So what are the other options other than per prefix?
So you have per link as well, but generally per link is not used much. Per prefix is what is generally deployed. So you can go for per prefix. In case of per prefix, the thing is each prefix can have a different path based on the cost, right? So per prefix gives you a very accurate FRR. Per link may not give you an accurate FRR. So we'll be concentrating on per prefix here because that is what is generally deployed.
Actually, just apology, if the cost was 10 all around, then there wouldn't be an alternate path.
There is no alternate path. Correct. There is no local LSA. If the cost was all 10 here, you don't have a local LSA. Because R2 will loop.
Cost is 100, right?
Between R1 and R2, now cost is 100.
Yeah. So even without LFA, only R1 convergence is the delay here, right? R2 anyways will send it through R2.
Okay. So two things. I mean, we'll come to that, but just getting ahead one slide, right? What happens is, now R1 has to, what R1 can do, it knows the primary path. Because you have enabled local LSA through configuration, it will run SPF on behalf of, with its directly connected neighbors as root and see if there is a local LSA available. If it is available, it will pre-program that in key. The Ceph will be pre-programmed, In hardware, it will pre-program it in keep.
Like a backup path, right?
Like a backup path. It's already pre-programmed in hardware. So when the primary path goes down, within about couple of milliseconds or so, it can switch, because now your delay is just a link down detection delay. After link down detection, there's a few microseconds for the ASIC, or in case of DNX, Ceph platform, the PD Ceph takes the call. PD Ceph makes the cut over. Okay, all that takes a few hundred microseconds.
So it will run that SPF only if it detects that R2 is running that perfect faster route.
No, R2 does not need to have anything enabled. So if you want R1 to do the protection, just have this local LFA config on R1 alone.
R1 only, okay.
Yeah, because now R1 has to send traffic to R2, right? R2 does not need to run local LFA. R2 just follows what is its best path in the routing table. That's it. This config is needed on R1 alone.
Okay.
So if
It
you
may not
enable,
be on every box.
ideally you should keep it on every box, because right now we are protecting just R1, R5 link for this example, right? But ideally you would like all links to be protected across all nodes. So have this config everywhere. That's the thing. Yeah, so if you have this config, then only R1 will calculate, it will run SPF with its directly connected neighbors as root, figure out if I have an alternate path, and then pre-program it in hardware. If you don't have this config, R1 is not going to do anything. R1 will follow the old way of.
Which algorithm is it used to find the backup path?
So the algorithm to find the backup path, I don't know what is, maybe some research paper somewhere. PQ algorithm will come to it, if that's what you're referring to. This is not.
EHRP uses dual algorithm, right? To find
So EHRP uses dual, OSPF uses SPF, ISI is also SPF. RLSA, I'm not sure what the algorithm is. It's not nowhere mentioned, must be in some university research paper. But the point is, the way it works is this. I don't want to get into too much complication here or provide too many details. My point is to keep it as simple as possible for you to understand how this works. Rest, if you need some details, you can figure out on your own. That's my point. But to your question, what is the algorithm like dual or SPF it runs to figure out, I'll get back to you.
It just checks if there is an LFA, right? If there is no LFA, it doesn't take
See, the algorithm is nothing. The algorithm just means you go to your look at your directly connected neighbors. The entire topology will have, R1 will have all the LSAs of R2. This is a link state protocol, right? Every router has everybody other's LSA. So every router can calculate SPF for any other router. So if you're asking for the algorithm, it's remote SPF. You can call it remote SPF because R1 is calculating SPF with R2 as root. I don't think there's any other algorithm. It's just remote. It's SPF again. But you're not calculating SPF for yourself. You're calculating SPF for your neighbor on you.
So if there is no LFA, does it make any change to the cost to make sure that loop is not happening? How does
So if you didn't have LFA enabled, right, R1 will not pre-program the backup path. So R1 will take that 100 millisecond or 200 milliseconds
and then
to
now
run
because it's
SPF.
not working, you move back to 4 into 10, one more.
It doesn't change the cost to 100.
4 into 10.
No. If the cost is 100 like this, then LFA does not change cost.
And made it work.
None of the FRR algorithms change cost. They work on what is the existing cost.
11:20
So
comes.
if LFA is there, then it forwards to R2.
Correct.
But if it's not there, what will the R1 do?
If it is not there, see, R1 has to eventually forward it to R2. There is no other way to reach the destination.
So what happened
the
now?
point is R2.
So,
Box or audio.
where is
Box or
configuring
WebEx,
this? Here, huh?
keep the audio mute.
On the R2.
I did that, but if somebody wants that, I can mute them all. Folks, on WebEx, kindly put your audio on mute unless you want to speak. Otherwise, I have to mute everybody.
you can't.
Actually, you can mute. When anybody has question, they'll unmute and ask.
Yeah, okay.
Krishna, when you're saying it runs the remote SPF, is it not running the local SPF also?
It has to run local SPF.
It has to do both for the primary path.
Exactly.
It has to do that, and for the backup path.
So it has to run a SPF with itself as root for the normal routing, right? That we can't avoid. But if you have to do LSA as well, then you have to run SPF as, with the route as your directly connected neighbors and figure out if they'll send the traffic back to you or not. But, fine, right?
Yeah.
Hey, if there are any questions on WebEx, feel free to ask. Yeah. Hope it's all good so far. It's quite simple, really. Yeah, so this is the thing. If you do show route to 150, which is my this destination, right? Is the pointer visible? Okay. So you see, it says gig 0001 is my backup, and it's via local LSA. Now we'll look at what the PQ algorithm is. Now again, consider the old network again, where all the link costs were 10. All right. Now R1 cannot have an FRR directly to R2 because R2 will loop it back till R2 can converge, right? Again, a couple of 100 milliseconds or 300 milliseconds or whatever, or maybe a second too. But R1 knows that if it can send, so we know, whatever, looking at this, that if we can somehow send traffic to R3, if we can fast reroute the traffic to R3, when R1, R5 link dies, R3 is not going to loop it back, right? R3 will send it to R4 and traffic will go fine. So this is remote LSA. And we note that there is a remote router somewhere in the network. If we can send traffic to it somehow, then it will not loop back to me. It will go on its way, and then I won't lose a lot of, it will be like sub 50 milliseconds. The whole point of FRR is to be sub 50 milliseconds. Why sub 50 milliseconds? It comes from optical networks. Apparently in optical, the cutover from primary to backup happens within 50 milliseconds. And that's when the standard was set. And all customers, when vendors were making FRR, they said, give me the same optical level of 50 millisecond cutover. So my applications which are built on 50 millisecond cutover tolerance will work. So that's the reason the 50 millisecond cutover, when that time came. Why 50 millisecond is because it's coming from the optical world. Yeah, so if R1 can somehow, coming back here, right? If R1 can somehow send traffic to R3, then R3 will send it. There won't be a loop, right? So now how to send traffic to R3? First of all, how to figure out for the router that R3 is the guy I need to somehow send traffic to. With that, you use PQ algorithm to get there. Again, let us see what the P space is. Okay, so concentrate on PQ because the rest of the session is based on PQ and any FRR that you see is based on PQ. So please concentrate here. P space is the set of routers R1 can reach without using the protected link. Let's consider this R1, R5 is a protected link. What are all the routers R1 can reach through its current routing table? What is its current best path? What are the routers it can reach without using R1, R5? Currently, what are the routers? If you look at them, I've already mentioned it, but it's R2 and R3, going purely based on the cost. So R1 to R2, cost is 10 directly. R1, R5, R4, R3, R2, the other path, cost is 40. So our best path, 10 is the best metric, so R1 can reach R2 directly without using the failed link or whatever the protected link. Similarly with R3, R1, R2, R3 cost is 20. But R1, R5, R4, R3 cost is 30. Yeah. So 20 wins, so R1 will not use R1, R5 link to go to R3. So far so good, right? Now if you look at R4, R1, R2, R3, R4, the cost is 30. R1, R5, R4, cost is 20. Right? So which means R1 will end up using the protected link to reach R4. So R4 is not in the P space. So you understood what is the P space, right? So all this just text explaining that. Now let us understand what is Q space. So P space again is set of all the routers that R1 can reach without using the protected link. Now what is Q space? Q space is the set of routers that can reach the protected prefix, whatever destination you're protecting, without using the failed link. Right? So if you look at say R2, what is R2's best path to reach 150.0.0.0? It is through the protected link, right? Because the metric is 20 from R2. Look at it from R3's perspective. For R3, what is the best path to reach the protected prefix? It is via R4. If R3 has to go via R3, R2, R1, R5, the cost is 30. But for R3 to go from R3, R4, R5, cost is only 20. Which means R3's best path does not use the protected link. So R3, similarly R4 too. So R3 and R4 are in the queue space. Now, so when I say PQ, what is PQ? I mean, I guess if you can make a guess, that people already know, don't answer. But people who don't know, who can make a guess, now what is PQ? Combination. It's like if you use sets in mathematics, right? What is the union or intersection? So R3 is the intersection here. So which means the whole point is R1 can reach R3 without using the failed link. That is its best path. And R3 can reach the destination without using the failed link. Our purpose is served, right? If R1 can somehow send traffic to R3, then R3 will send it. There's no chance of a loop here. So what we understand implicitly is, I mean, the same thing, router runs the PQ algorithm to arrive that I need to somehow send traffic to R3, then R3 will send it. That's PQ algorithm. It's quite simple. Any questions on WebEx so far? All good, I'm assuming. Okay, moving on. If you have a question, feel free to interrupt. So no worries there. Okay, so now how does R1 send traffic to R3? I mean, so R3 is remote, right? R3 is not directly connected, so that's why this is called remote LFA. Local LFA, you could send traffic to your directly connected neighbor. That's why it is local. It is locally connected to you. But in this case, R3 is not locally connected, it's remote, so remote LFA. Okay, so we generally tunnel everything, right? If we have to send to some other destination, we tunnel it. The whole point is tunnel traffic somehow to R3. But that's the whole point. Now, the question is what sort of tunnel to use. We have multiple tunneling options, right? We have GRE, we have BPWS, we use targeted LDP. That's one tunneling solution. We have GRE available. And think of any other option. What is chosen here is to use targeted LDP because you already have LDP running in your network. So this came before segment routing. RLFA is there since many years, even before segment routing thing. Back then, all the networks had MPLS enabled, right? So use targeted LDP because you already have LDP running. For local LFA, you don't need MPLS. Local LFA runs purely, I mean, just normal IPv4 routing or IPv6 routing is enough. You don't need MPLS. But for RLFA, you need a tunneling solution. The tunneling solution we thought we'll use is targeted LDP because it's the simplest thing. Since your network already is MPLS enabled. Alright? So once R1 figures out that R3 is my PQ node, R1 will initiate a targeted LDP session to the PQ node. Yeah, that's it. So R1 initiates a targeted LDP session to R3. R3, since it's running LDP already, it will have some label for 150.0.0.0, right? It will have some label in the table. So R3 will advertise the same label to R1 via the targeted LDP. The point is, when R3 receives traffic, it has to receive traffic with its label for 150.0.0.0. Then it will forward it to R4. So whether that traffic, say, label is X, whether R1 is sending or R2 is sending or somebody else is sending, if they send with label X, R3 in its forwarding table knows that and just send it to R4. Normal MPLS switching. So that's the reason R3 advertises label X via the targeted LDP session to R1. That bit is done. But now R1 has to somehow reach R3, right? How does it do that? R1, so in this case it will use two labels. The bottom label is label X, what R3 gave it to reach 150.0.0.0. So the top label will be for R1 to reach R3. Because we have to reach R3, reach the remote node. So in that case what happens is, say R3 is loopback, the TLDP session is between loopbacks. Now R3's loopback is 3333, which is advertised to R2 as well. R2 would have generated a label for 3333 and R2 will advertise it to R1. So all R1 does, say R2 advertises label Y for 3333. R1 will use a top label of Y and a bottom label of X. Top label of Y ensures that the traffic will reach R3. Bottom label of X ensures that R3 will forward it to the destination. So if R1 sends traffic with top label Y to R2, In this case, R2 will just pop the label because R3 is directly connected, right? So far with me on this? R3 will receive a packet with label X directly. Now what if R2 and R3 were not directly connected? Then say there is a R 2.5 in between. Now R2 will swap label Y with whatever label R 2.5 gave it to reach 3333. This is a normal LDP forwarding thing. So top label Y to reach R3, bottom label X for R3 to send it to R5. Any questions so far? All good? Or any question on the WebEx? All good?
Will be same. Top level will switch. I mean, it's just the transport label.
Top label is just a transport label. If you already know how VPLS, VPWS, L3 VPN works, the top label is always to reach.
Yeah.
Similarly, the top label is to reach my PQ node. That's it.
The two label scenario is only during the sub-second, or it is over the complete period?
Okay. It is sub-second in the sense, okay, so once R1 figures out that R3 is my PQ node and I need to use two labels, it will pre-program that in FRR, in the hardware. As soon as the link down is detected, it will cut over within few milliseconds. I think sometimes we see within 1 or 2 milliseconds it cuts over. Sometimes we have seen 0 milliseconds also. When Spirent was 0 packet drop, as in 0 millisecond convergence, but it's not 0, in microseconds it has done the cutover. So we don't see anything in milli. So to your question was?
Like, as long as it takes a backup path, on my transport network, I will always see two transport labels.
Exactly. Till it reaches R3. You will see that. So there is something called micro loops. We'll come to that at the end. Alright. So if you understood what I've covered so far, that's good enough for now. We'll see all the complications or whatever arise later.
So far, whatever we have seen, the PQ algorithm itself takes care of what is the manual config?
So here, config I'll come to. You enable that config line, R1 will automatically run the PQ algorithm, build the targeted LDP session once it figures out who the PQ is and all.
So the figuring out the intersection node and forming a TLDP
is all automatic.
It's all automatic.
It's just one line config. So the RLSA or IPFR config is dead simple, 1 or 2 lines. But what happens in the backend as a result of the config is a lot of process.
And this PQ algorithm is common for OSPF for ASIs.
Yeah, so PQ algorithm is independent of OSPF or ISI. You enable RLSA in OSPF, it will do the same thing. You enable it with ISIs, it will do the same thing. Then it will tell the MPLS process to start a TLDP session, get the label, and program it in hardware. Got it, right?
Krishna, one thing. So switching from primary to backup is 50 milliseconds guaranteed.
Yeah.
But backup to primary?
So backup to primary.
Do we still guarantee 50 milliseconds, or that is purely?
So generally, if it is okay, so when you say backup to primary means it's a less high cost path to you're trying to go back to a low cost path whenever a low cost path is available, right? That's always make before break.
Yes.
Ideally, you should not see any drop.
Yeah, 50 milliseconds.
We say 50, but ideally it should be 0 as per theory, right? See, in this case, what happens is the link is down. You don't control that the link is down. You got notified that the link went down. It's not in your control, right? But if you're already going via a backup path, you got a better path available now. It's totally in your control how you want to switch to the better path. So what happens is the better path is calculated, programmed in hardware, then the switch is immediately done.
So you mean to say 0 packet drop?
Ideally it should be 0, but the real world, tolerated value is 50 milliseconds, even for that. Anything 50 milliseconds means your applications are not going to see a glitch. That's the whole point. But ideally, if you're doing a re-opt, that's a re-optimization case. It's called re-opt case. Going from a high cost path to a low cost path is always make before break. Should be 0 ideally, but 50 milliseconds is accepted. No problem. Okay, moving on. The config again is you have to enable targeted hello accept because that's a targeted LDP. Without this targeted LDP sessions don't form, right? You need to have this so that targeted LDP forms. And how do you enable RLFA under the interfaces? You have to enable fast3.per prefix. You have to enable this config, local LFA. Then you say fast3.per prefix, remote LFA, tunnel is MPLS LDP, as in you're doing a targeted LDP session. Now you may ask a question, what happens if I have both local LSA and remote LSA enabled? And say you have a local LSA path and a RLSA path, as in your network is such that both are available to you. What will you choose? Local LSA. Why would you choose local LSA over remote LSA?
Avoid the tunneling as much.
I mean, yeah, avoid the tunneling, avoid an extra label. So the whole point is efficiency, right? With local LSA, you need not push any extra label stack. Whatever your label stack is, you just send it out of a different interface, that's all. But if you do RLSA, you have to add an extra label, build a TLDP session. So, generally you have local LSA enabled always. Along with local LSA, you will have RLSA or TI LSA. That's the way it works. And if local LSA is available, always prefer local LSA. Even if you have RLSA or TI LSA path. Just for efficiency's sake.
Programming alone doesn't take care of, whatever gets programmed.
So all this is done at the PI level. If PI decides local LSA, then accordingly hardware is programmed. If PI decides RLSA, then hardware will be programmed. It's all done at the PI level. Hardware just, PI decides and then just pushes the program to hardware. Hardware just has to take what PI gives. Hardware has no intelligence of all this.
My question was if I enable both, so this is taken care at the programming level itself, right?
Yes. Yes. It's taken care at PI and PD level.
You're going to cover TI LSA?
Yes. The reason I wanted to show all this is to show the limitations here and then how TI LSA addresses those limitations. Otherwise, you won't really appreciate what TI LSA is. Right? That's all. So far so good, I hope. Right?
Krishna, one question here.
Yeah.
Krishna, see, I know it might be out of topic. See, do we have any scale limit like the 9K or XR box can protect only these number of with respect to RLSA?
So I think even in this case, your limit will be based on hardware. Say, in case of DNX platforms, right? We have only, I think, 96K NCAPs.
Okay.
Or I think 128K out of which 96 are usable or something like that. So your primary path will end up using an NCAP or maybe more. Your backup path will also end up using one NCAP or more. Generally one NCAP. So if you have 48K prefixes and you have to end up protecting, then your hardware NCAP, you will be crossing your hardware NCAP limit. So I think hardware is where your limitation will come.
But not with respect to the prefix count which you are protecting, correct?
No.
Okay, and one more question. Like, I just want to know, is there any way that we can say we are receiving some around 5K prefixes in the IGP, and you want to protect only few of them, not all the 5K, might be around 2K of them. Is there any way? See, I know it's not a right time to ask this question, but see, in XE world, like what we do is we create a route map and then you assign that route map.
I think you have a route policy here. In XR world, you can have a route policy.
I tried that, but I was not able to get that working.
Okay, let me try and get back to you then. I think there is a way. Yeah.
If you can get back to me on that, it would be really helpful.
Sure.
Yeah, thanks, sir.
So Krishna,
yeah, go ahead.
LFA is, as of today, it's only supported with LDP. Like you cannot have a.
If you don't have LDP, it's not going to work. So local LFA doesn't need LDP. Just plain IP is enough. But for RLSA, you need LDP, and it's primarily targeted at service providers where LDP is enabled anyway. So this is a config. Enable local LSA, then enable RLSA. Automatically, it takes care of the rest. So the point is, wherever
is that keyword tunnel MPLS LDP there? If only LDP is.
So tunnel MPLS LDP, I don't think there are other options. You know, question mark and see. I don't think there are other options because targeted LDP is the only way RLSA is done currently. Yeah. So the thing is, you need to have this discovery targeted hello accept on all routers because you never know which ends up becoming your PQ. Because the PQ router has to accept the targeted LDP session from the source node, have this discovery targeted hello accept on all routers. Okay, but this RLSA config you need to have only on the source. But ideally, people put it everywhere because you have to protect all your links, all your prefixes, right? But if you just want to protect this one single prefix, have targeted hello accept on all routers, and then have RLFA config on the source. Okay.
One thing, so how the hello packet is different from a regular LDP and targeted? Will there be a change in the field also?
Targeted
Also,
LDP,
if I enable MPLS everywhere, right, I accept my hello packets. And TCP session will get established. 646 is the port
correct,
number, right? So for targeted LDP also, I'm going to use the same
yeah,
TCP
targeted,
session.
so
how different, why I have to use this command? So it's going to be a simple LDP packet only, right?
no, so the thing is, the reason I have to use targeted LDP is, how does R1 know that it has to put label X? So you know, right, R3's label to reach 150.0.0.0 is X, right? How will R1 get to know that that is R3's label? How will R1 know that I have to push label X? R2 will not tell it because R2 will give its label to reach the destination, which may be some other label. But R1 has to push label X, which is R3's label. The only way currently, or the best way they designed is, have a targeted LDP session between R3 and R1. Let R3 tell R1 that this is my label. Got it? So in BPWS case, you exchange the VC label over targeted LDP, right? Similarly, here you exchange the R3 sends its label to R1. Because there is no other way for for R1 to get to know what is R3's label to reach the destination. You need a targeted LDP session for that.
And is there any chance like 2 nodes can be PQ?
Yeah.
So
you can have multiple nodes as PQ.
okay.
In what I have seen in RLFA cases, whatever is nearest to the source, it ends up picking that.
Okay.
In TILFA case, we have seen the reverse. Whatever is nearest to the destination, but TLFA is slightly different. We'll get to it. In case of RLFA, generally it's the nearest PQ node because the label stack may be the least, or you don't have to send packets with lot of labels for a long path. Say your PQ node is R4. Can R4 be a PQ node? It can't be in this topo. But say R4 was a PQ node. Then in that case, you have to send 2 label packet to R2. R2 will have to send 2 label packet to R3. And then to R4, right? So you have sent 2 label packet over an extra link. But if you choose the nearest, you have to send 2 label packet only to R2. Just efficiency, nothing more. Wherever you can save it. This is what I've seen. Yeah. Again, the same thing. The command to check is show ISIS fast reroute whatever prefix detail on R1. It's telling that my RLFA or the PQ node is R3. What we discussed. This is its loopback, so it will form a targeted LDP session to this loopback. Then you do show MPLS LDP neighbor. You see there's a targeted hello from 1111 to 3333. So R1 has initiated a targeted LDP to R3. This is what this command says. And then, okay. And then if you see here, what is R3's local label? To reach the protected prefix, it is 24002. I'm checking on R3. So which means R1 has to know that I have to put 24002 as my bottom label, right? So now R2's local label for 3333 is 24,000, which means when R1, the top label, when R1 is sending traffic to R2, it has to use label 24,000 for R2 to send it to R3. Because it has to reach R3, right? That's the transport label. So these are the 2 labels. Remember 24,002 will be a bottom label and 24,000 will be a top label. You check the Ceph. I mean, show route also will show this, but I thought show Ceph because it's a bit more granular output. Show Ceph for 150 for the protected prefix. You see that your protected path is your primary path here. Primary path says go directly to R5. But your backup path, it says impose a bottom label of 24,002, top label of 24,000. And these labels have come here. 24,000 is my top label, which is R2's label to R3. 24,002 is R3's label to reach the destination, which R1 learned via targeted LDP. That's it. Okay. Now we look at what is extended PQ. So why extended PQ? Again, now we have a 6 router topology. Now, in this case, can you tell me what are the P nodes? Link cost is 15 here, remember? It's 10 everywhere else, just between R3 and R4 it's 15. R2, R3 are the P space, right? What is the Q space?
R4, R5, R4,
R4, R5, right? So agree, everybody, that P space is R2, R3 and Q space is R4, R5? We don't have a PQ intersection here, right? So can you do RLFA?
I need to R4.
So the thing is,
Yeah, we don't have a PQ space.
we don't have a PQ space because it's R1, it can't send it to R4 because R1's best path to reach is via this, right? It doesn't satisfy the P condition. So you don't, now okay. Now what if you did PQ from R2's perspective? I mean P, at least P from RQ's perspective.
R4 will be your.
So R3, R4 are my P space from R2's perspective. Correct? What is the Q space? Remains the same, R4, R5 from R1. So Q space is from R1, that's fine. But P space from R2 is R3, R4. Do I have a common PQ now? R4, right? So the reason it works is, so R1 will run the PQ algorithm from R2's perspective. So R1 will run P algorithm from its directly connected neighbors. The reason it does that is, if R1 knows that I can send traffic to R2, and then R2 will ensure that it reaches the PQ node, am I good? Right? So this is called extended P space, where I run P algorithm from my directly connected neighbor's perspective. So if my extended P and my Q space have an intersection, I'm still good, because the whole point is packet will not come back to me. I need to send it to my neighbor. That guy will ensure it goes to PQ space. Without coming back to me, I'm good. Right? That's the whole point of extended P, Q, and then the combination is extended PQ. Same thing here. R1's P space is R2, R3. R1's Q space is R4, R5. Alright, no common PQ node, so RLFA not possible here. Now calculate P space of your directly connected neighbors. This becomes the extended P space. If R2 can get a PQ node, R1 just needs to send traffic to R2. R2 will ensure it reaches the PQ node without loopback. So now you calculate P space from R2's perspective. It is R3, R4. Q space of R1 is anyway R4, R5. And then you have extended PQ, which is R4. So all R1 needs to do now is put the transport label of R4, the top label to reach R4, and then have a targeted NDP session between R1 and R4 so that R4 can advertise its label for the destination to R1. So bottom label can be R4's label to reach destination, top label is to reach R4. Alright, so this is, again, this is a small extension to the existing PQ, becomes extended PQ. The same method again, assume that R4's label is X, and then R2's label is Y. So top label of Y to reach R4, so R2 is advertising the label of Y to reach R4, 4444. So R1 needs to put a top label of Y and a bottom label of X. How did R1 learn X? Through targeted LDP to R4. So if R1 sends top label Y, bottom label X to R2, what R2 will do? R2 has to swap it with R3's label for 4444. Right? Say R3 has advertised label Z for 4444 to R2. R2 advertised label Y. R1 will send with label Y. R2 will have to swap Y with Z to send it to R3. Right? And then R3 will just pop the top label. R4 will receive a packet with just label X, which is its label to reach the destination. Program this in hardware, pre-program it, FRR is ready. Got it, right? So far so good. On the WebEx, so far so good. Let me know if you have any questions. Probably move on.
Do you have the step output for this particular system?
Yeah. So this is the thing. You have this blue line just represents a tunnel. Tunnel as in my top label is to somehow reach R4. Blue line represents to reach PQ. Once it reaches PQ, it will go on to its destination. Again, right?
LDP session should happen between R2 or R4 or R1 or R4. I think packet you have sent to R2 right now.
I've sent to R2. So R1 has calculated that R4 is in my extended PQ space. My extended PQ node is, so R1 calculates, R2 doesn't do anything. But R1 has run the P algorithm with R2 as root. Remember in local LFA, R1 ran SPF with R2 as root. But it ran it on itself to understand what R2 will do.
So it's not sending packets to R2 at all.
So it has to send packet to R2. See, physically it has to go through R2. There's no other way, right? My physical link is to R2 only. Correct, right? But I'll put the top label as R2's label for R4. My top label should be that somehow I reach R4. Maybe these dotted lines have caused the confusion. But the point is, top label, somehow, the reason I put dotted line is because it's a tunnel. I have to tunnel traffic somehow to R4.
Okay, what I thought like it will send to R2 and then it will start that PQ thing.
No. So, local LFA, RLFA, PQ, extended PQ, all of that is running only on R1. R1 is running SPF with R2 as root, or R1 is running P algorithm with R2 as the root node. On R2, R3, R4, R5 and R6, I just need to have targeted hello accept for the targeted, for all of these routers to accept targeted LDP session from R1. That's the only config needed on them. They don't do anything else. RLFA config is not needed on all of them. Only on R1, RLFA is needed.
R4 does not know I'm extended P or not.
R4 does not know. Nobody else knows. Just that once R1 decides R4 is my extended PQ, R4 has to be ready to accept the targeted LDP session coming in from R1. For that, I need to have discovery targeted hello accept config. Otherwise, R4 will not accept. That's only. But again, as I said, you will enable this everywhere because you want to protect all links, all prefixes. But for this session, R1 alone. R1 alone is doing the P, Q, RLFA, LFA, everything. Nobody else is even aware.
So the PQ node in general, can we say that as the closest node which has the reachability to the destination,
Correct.
which is not taking the
protected path, that is Q space. And for the source to reach that node, which is the P space, it should not take the protected link.
Yeah. Right.
Well, right, that's it. Again, look at the command, show ISI as fast reroute. In this case, R4 is my RLFA, which is the extended PQ node. It doesn't say extended PQ and all that. These are just algorithms. It says my RLFA is from R4. If I can reach R4, it will send it via R4. So R1 initiates a targeted LDP session to R4. All right. So in this case, I captured the actual labels. R4's label is 24001 for the protected prefix. I'll show this. Okay, R4's local label for my destination is 24001. Alright, so if R4 receives the packet with 24001, it will send it to the destination. That's the whole point. And R4 will advertise the same label via targeted LDP to R1. What is R3's label to reach R4's loopback? It is 24000. Which means if anybody sends packet with top label 24000, R3 will send it to R4. Which means R2 has to send packet with 24000 to R3. What is R2's label? It's 24001. Which means R1 has to send packet with 24001 to R2. R2 will swap it with 24000. R3 will pop it. Packet reaches R4. And when packet reaches R4, it reaches with the bottom label of 24001, which is R4's label. Then the packet goes. Alright. So if you look at the same thing, show step. My primary path is via R1, R6, and my backup path has top label 24000 because that is R2's label to reach R4. Bottom label also 24000. In this case, they ended up being the same, which is R4's label to go to the destination. Alright. So this is extended PQ. Hope this is fine so far in WebEx as well. Any questions? Feel free to interrupt. So RLFA can't solve all problems. Even with extended PQ, you can't solve all problems. Look at this link. Just do extended PQ. Do you have, what is the extended P space?
R3 and 4.
The extended P space is
R3, R4, R5.
Yeah, R4, R5.
R3, R4, R5?
Yeah.
That's my P space. What is my Q space?
Space for R1, right?
No, there's.
Do we have a Q space here at all?
You don't have to.
See, R5 is the nearest router to R6, but what is R5's best path to destination? It's
Again has to come back.
R5's best path is again R4, R3, R2, R1, right? Cost based. You don't have a PQ here. Even if you ended up using extended PQ, you still don't have a Q. You don't have a Q. The problem is, you do P, extended P, whatever. Point is you don't have a Q here. Because you don't have a Q, you can't form an intersection at all of PQ, right? So RLFA fails here. This is the problem with RLFA. RLFA gives 85% coverage because most of the deployments you have seen RJL or whatever, generally they are ring. So RLFA works in most cases, but then there are cases where RLFA can't give protection due to this reason. Because you don't have a Q space here, alright? Same thing, you have a P, I mean this is R1's P space, R2's P space is just R3, R4, R5. You don't have a Q here. Now this is why TLFA can solve this problem. So TLFA, the reason it's TI is topology independent. I don't care what the topology is, I'll give you 100% FRR coverage, no matter what network you throw at me. That's why TLFA solves this problem. I mean, how it solves we are going to see. This is where topology independent LFA comes in, 100% FRR coverage for any network. Let's see how.
There is no limitation for 100%.
100%, what you give any network, whatever cost on any link, TLFA will give you FRR.
But that depends on the platform also, right? Depends on how many people can push.
Yes. That limitation will come. See, but generally we talk about, I'll come there. 99.9% of the networks, 2 labels are enough. 2 extra FRR labels. In RLFA case, what we saw 1 extra label, right? Which is a transport label to reach the PQ node. From PQ node onwards, it's a normal forwarding, one single label. In case of TILFA, max you've seen is two labels to reach the PQ. You can do 3 as well, but I mean exceedingly rare that you need 3. 2 is good enough generally. So with the current limitation of ASIC, as in the label push limitation, TLFA will still give you 99.999% network coverage. And now of course it's increasing. Now 11 label push in DNX using recirculation, it will recirculate. So I don't think that's a problem now. Again, I hope you remember node SIDs and adjacency SIDs. Yeah. Right? So again, just make a note of the node SIDs. R1 is 16,001, R2 16,002, R3 16,003, R4 16,004, 5 is 16,005, and 6 is 16,006. Adjacency SIDs are dynamically allocated, if you remember. Though we can manually give it, by default they're dynamically allocated. Node SIDs are manually given. Right? So these are the adjacency SIDs as per the topo that I mean, when I was doing the lab, these were my adjacency SIDs and I've noted it down here. Because whatever output you see later, right, it will be based on these things. Alright? Now we look at what is single segment TILFA. Single segment is the same as RLFA, where you have one label to reach the PQ node. If using one label you can reach your PQ node, that's single segment. And then you're adding one single segment ID to reach PQ node. The same thing, same extended P space, Q space. Alright. R4 is my extended PQ node. So what R1 has to do, R1 has to somehow reach R4 and then go on to the destination. Now note that my destination is 6666 because, as I said it, in segment routing we don't assign labels to prefixes. We assign labels only to the nodes. So in this case I've kept my node as a, but this doesn't mean that it won't protect 150.0.0.0. You remember 150.0.0.0 was my protected prefix in this case. So TILFA protects these prefixes also. So TILFA will see this prefix is connected to what node. In this case it is R6. So what TILFA will do, it will try to build PQ node to reach the node where my destination prefix is connected. So that way I end up protecting this also. Right? So TLFA protects normal IP, so RLFA doesn't protect normal IP traffic. It's only labeled traffic generally. TLFA protects labeled traffic, which will be my node SIDs. It will also protect unlabeled, which is my prefixes here. Anyway, we getting back. Now I'm trying to protect 6666, which is my loopback of R6. Okay. Same thing. from R1's perspective, extended P space is R3, R4, Q space is R4, R5. My R4 is my extended PQ. Now, and I want to reach 16,006. I mean 6666. Can you tell me what is the label stack here? Can you kind of think what could be the label stack? What is R1's first purpose? To somehow reach R4 and then reach R6. So what do you think will be the top label, bottom label?
Top 16,004.
Bottom?
16 over 16 over 6.
Correct. So on WebEx as well, I hope that's clear, right? So in this case, the top label will be 16,004 because I have to reach R4. And then the bottom label will be 16,006 for R4 to send it to R6. Hope this is clear, right?
Yeah.
This is exactly what happens. Anyway, the config is fast readout per prefix, local LSA has to be enabled. No targeted LDP session here, remember. So this is another advantage of TLSA is that you don't do targeted LDP. So R4, which is the extended PQ, does not even know that it is the extended PQ now. At least in RLSA case, on R4 there was a targeted LDP session built. So indirectly, you can know that R4 is the PQ node because you have a targeted LDP session on it. In case of TLFA, that is also not there because of the node sits and adjacency sits. So R4 doesn't even know, or there's no change on R4, even though it's a PQ node.
So label swapping will happen at both R2 and R3 with the same label number.
Exactly. That's a segment routing swap that we discussed in the last session. Okay. Enable local LSA and then enable TILSA. This is the config. No need of targeted discovery, hello, accept, blah, because there's no targeted LDP. There's no explicit tunneling mechanism used here at all. It's all implicit tunneling. Alright? So 16,006 is the label for 6666. This I'm seeing on R1. R4 is the PQ node. Again, if you do show ISI as fast readout, it will still calculate the PQ node. PQ doesn't change. The whole point is how to reach P and then, how to reach PQ and then the destination, only those labels are changing. And the method to reach is changing. That's all. So again, it's R4 is my PQ node. Label is 16,004. Alright. And if I check show set for my destination, my protected link is R1, R5. My backup, now this is via TILSA. It says TILSA here. And then the labels imposed. Bottom label is 16,006. Top label is 16,004. This is also known as single segment because there is one label you're pushing for transport. This is as good as RLFA. RLFA is also, there's no segment concept in RLFA because it's traditional MPLS. But if you were to compare, RLFA is like single segment TILSA because one transport label is pushed. Same thing, R4, R1 will send with label 16,004 to R2. R2 will swap it with 16,004 sent to R3. R3 will pop 16,004 because R4 is directly connected. R4 receives packet with 16,006. R4 will send it to R5 and then R6. Clear, right? So far so good. On WebEx also, I hope so far so good. Again, any questions? Feel free to interrupt. Yeah. Now we see what is double segment. So this is the TILSA magic actually. This is what RLFA can't achieve, TILSA can achieve. From double segment onwards, it's TILSA speciality, which which local LFA or RLFA can't do. Again, the same thing. Now assume that the link cost in between here is 100, between R3 and R4. Alright, you don't have so the P and Q spaces are different. If you want, I'll just be on the slide for about 30 seconds. You can mentally calculate what is the P, Q, or even extended P and Q. Alright, so point is you don't have a PQ. You can take some time and then just.
This is the same case as what previously R5 to R6 link was.
Exactly.
But in that case also PQ was not there.
Was not there.
Also, even with R2 also we are not having PQ.
So in that case, there is no Q at all. But in this case, we do have a Q. We do have a P. Even if you run extended P algorithm, we do have extended P and we have a Q. Point is, we don't have an intersection. In the previous case, there's no Q at all. In this case, we don't have an intersection no matter what you do. So RLFA will fail here as well. How will TILSA solve this? Can you think? Very simple.
we put the segment label that link label from R3 to reach R4.
It's a simple solution actually. It's nothing complicated. Got it, right? The whole point is R1. So R1 has to push the adjacency set of R3 R4 link. Then what R3 will do? R3 will just blindly push it and send it to R4 because it got with that top label, right? That's what. So TLSA gives you 100% coverage because of adjacency sets. So now you're beginning to see that how adjacency sets are helping in this cause.
Hey, Krishna, I didn't get it. So now in this case, what will be my what will be my top label?
Top label. So I don't have a PQ here. Okay.
Yeah, I don't have
Okay.
it now.
So in this case, what my top label will be to reach my farthest P node. I don't have a PQ. Somehow reach my farthest P node, which is R3. R3 is my farthest P node, right? Which is far away. And what is my nearest Q node? R4. So if I can somehow push adjacency 6 so that my farthest P node can reach my nearest Q node, right? Then Q will send it to the destination.
So my top label will be my adjacency node between R3 and R4.
No. So, okay, adjacency sets are local, right? If I push top label as my adjacency set, it will just drop because
I don't have it.
But my top label, if I push to reach R3, top label is R3, my middle label is adjacency set. So with top label R3, somehow I am ensuring that my packet reaches R3. Once packet reaches R3, the adjacency set which is local to R3, R3 knows to push it to R4. Getting it right? How the label stack will be built. And then my bottom label is to reach the destination, to 16,006.
So how does R1 knows this is when we enable TLFA it calculates?
It does all of that automatically. It will try to form PQ. If PQ is there, single segment TLFA, very simple. If before that local LFA is present, TLFA will not even be used. Right? If I don't have a PQ, then R1 will see what is my farthest P, nearest Q, and somehow try to tunnel between them using adjacency sets.
In this case there will be 3 labels.
There will be 3 labels. That's why it's a double segment TLFA because I have 2 transport labels to reach my Q node somehow. That's why double segment. And then of course I have my.
So is there a possibility that this R3 and R4 in this case the farthest P and the nearest Q are directly connected? But
They need not be directly connected. Say assume in this case, okay, that R5 is my nearest Q. Say I have a topo. Okay, going back to this topo, just assume that my farthest P is R3 and my nearest Q is R5. So R4 is not in P or Q, which means I have R3, R4 and R4, R5 to travel to reach my Q from P, right? Then in that case, what do I do? Can you tell me what prefix it of? So it's
R4 and then R3 and then R4.
If I put R3 and then R5, okay, I reach R3, say this link here has cost 100, R3, R4 link has cost 100, and R4, R5 link has cost 200. Then R3's best part to reach R5 is again back via R1.
So two adjacencies.
Two adjacency sets. Put R3, R4 adjacency set and then put R4, R5 adjacency set. That becomes 3 segment TLFA. But it's exceptionally rare to see 3 segments. No matter what network you throw at it, right? I mean, I tried 3 segment once. I had to think for half a day what cost to put where in the network to achieve it. It's very difficult for you to get a condition where you have to use 3 segments. 2 segment is relatively easy. Single segment is straightforward. Got it, right? 3 segment, 4 segment, go on. But point is, in real networks, more than 2 segment you may not see. I hope this is fine on the WebEx side. Again, at the risk of repeating myself too many times, interrupt me when you need to. Okay, too far ahead.
Specific to segment routing.
Yes.
It cannot work on its own.
Without segment routing because it needs adjacency sets, right? So you get adjacency sets only if you enable SR. Without that you don't. So it is dependent. I mean, you need to have SR enabled.
So RLFA and DLFA you can enable together?
You can enable together. I don't think there's a restriction there. But I think if
preference would be.
I think preference is again depending on whether LDP or SR. This I have not tested.
It's the same command, right? But why do we need both? Anyhow, it is
I think that's
You need both.
No, if you already have, and then migrate, I mean, just thinking about it.
Again, to let you know, right, as I told you, TLFA just doesn't protect SR labeled prefixes. It protects plain IP. It also protects LDP. You don't need.
Anyway, the label space is completely different, so it don't interrupt, right?
Correct. So you can have LDP and SR enabled. You don't need RLFA enabled. You just enable TLFA. TLFA will also protect LDP prefix.
No, but how do you, that block is different, right?
No, block is different, but it's all about pushing label, right? R1 needs to know what label I have to push so that I go there. So say in this case, R4's label to reach the destination is not SR label, but it's a LDP label.
Okay.
Assume. Okay. So in its label stack, R1 has to reach R3, top label to reach R3, middle label R3, R4 adjacency set, bottom label is R4's LDP label. It will still go, right?
That is fine, but I think it will be looking for the label space that we define globally for segment routing, right?
No, that need not be. See, so the global space for segment routing is to assign SR labels. Your LDP is different, but you have a label, you have a value. I just need to push those values. It can be a combination of SR and LDP labels. Point is, will I reach my destination if I push those combinations? You can, right? So TLFA protects plain IP, it protects LDP also, it protects SR anyway. So if you have LDP and SR enabled, just enable TLFA. You don't need to have RLFA. TLFA will protect that also.
Hey, I have one question.
Yeah.
Actually, if we enable LDP and SR both, and if you don't give that SR level preferred, then LDP will work, right, end to end. But however, if we give the SR level preferred, then segment routing will take precedence, and it will in the forwarding will have all the SR levels, right?
Correct.
So in that case, is there any practical possibility of the scenario that you told just now? LDP and SR will combine.
See, this I have not tried, but I have read that SR does protect LDP prefixes, and theoretically, right, say R3's label, I mean somehow to reach R3 on R1, say label 64,000, which is an LDP, okay? Between R3, R4, you push the adjacency set. And from R4 again you push the LDP label to reach destination, say 64,001. So you have top label 64,000 to reach R3, adjacency set in between to reach R3, R4, and then R4 put the destinations label. So this is, I have not labbed this particular scenario, but I have read that SR also protects LDP.
Yeah, that's what I was thinking. In R4, if we don't give SR level preferred, then definitely LDP level will take precedence, and in that case, there will be no adjacency set between R3 and R4, right?
No, adjacency set will be there. See, you have enabled SR, right? As soon as you enable SR, node set adjacency sets will be generated, irrespective of whether SR is preferred or
Will it be
LDP is
used
preferred.
in the forwarding table? That's the question, right? Will it be used in the forwarding?
In the forwarding table, both LDP and SR prefixes are programmed, or labels are programmed.
Correct. But if we don't give that SR level preferred, then LDP level will be used.
No, so LDP label will be used. That part is correct.
For forwarding.
Correct.
So that's
that
the
part
confusion actually. This I wanted to clarify what will happen in case.
Okay. Let's look at it that way. Okay. I think I have to open my previous presentation. Shall I open it now or shall I take it up at the end?
You said that if it is coming with SR level and even if even if LDP prefer is configured, then also it will go with SR level.
SR because it's already programmed in my hardware.
So I think his question is that only, right?
Exactly.
On R4, if we are having LDP preferred, but if packet is coming with
SR
SR level
level.
from R3, then it will go with SR level only.
Exactly. Because both LDP and SR are programmed in hardware. Does that answer your question, Abhijit, or shall I take it up offline with you?
Maybe offline, yeah. You can proceed.
Okay. Yeah. Okay.
Krishna, one question here, Swami here. So how does the R1 know the adjacency set of R3 to R4?
Okay. The thing is, it's just LSA generation, right? When R3 generates OSPF LSAs or ISIS LSP, the traditional IGP way, it also includes the adjacency set. So when R3 generates an LSA describing its link to R4, it will say what is the cost, then it will say what is the neighbor connection.
So every router in the node knows every adjacency set.
Yeah. Every router in the topology knows every other router's node sets and adjacency sets.
Okay, fine. Thanks.
Because IGP floods it.
Sure.
Fine, right?
Yeah, fine.
Okay.
Thanks, Krishna.
Yeah, no problem. We'll move. Okay, so in this case, P and Q nodes are disjoint, right? So if you do show ISI as fast state out, it says my P node is R3, my Q node is R4. I don't have a common PQ, right? And then what is my label to reach the P node? 16,003, which is a node set of R3. What is the label to reach my Q node? It is actually the adjacency set, 24,014. You see, right? So that means the transport label for FRR here will be top label 16,003 to reach R3, middle label, I'll call it middle label for now, middle label 24,014 for R3 to send it to R4. That's what it's saying. And as usual, 16,006 is the label to reach my destination, which is 6666. Now if you do show steps, primary path R1, R6, you see backup is TILSA, labels imposed, top label 16,003, middle label 24,014, bottom label 16,006. Fine, right? Label stack, good. This is double segment TILSA. First segment to reach P node, second segment put P, adjacency set of P node to reach Q node. I mean, P is adjacency set to reach Q. If P and Q are many routers apart, keep putting as many adjacency sets to somehow reach Q.
So R3 will be having for 24,012, 24,014, R3 will be having POP. It's
Exactly.
not going to send with that.
Exactly. So what R2 will do? So R1 will send with 3 labels to R2. R2 will pop 16,003 because R3 is directly connected, right? R2 will send 24,014 and 16,006 to R3, 2 labels. R3 has received a top label 24,014, which is its adjacency set to go to R4, right? So R3 will pop 24,014. R4 will receive a single labeled packet, which is 16,006, send it to destination. Okay, so far so good, I hope. Okay, now we come to the last section. Understand what are micro loops. Okay. So again, we consider the same topology. All right. At t is equal to 0, link went down. R1, say within 5 milliseconds, it did the cutover. It sent traffic to R4. All right. So it did that. And then say R1 takes 150 milliseconds to converge. Now, this link went down, right? The normal IGP convergence will happen. IGP will recalculate SPF, figure out what is my best path to reach the destination, and that is to R2 now, because I don't have link R1, R5 link. My normal IGP best path post convergence will be R1, R2. Getting that? Right? So that is assumed taken 150 milliseconds. Okay? So within 5 milliseconds, R1 was able to switch it to the PQ node, or in this case, there is whatever, R4 is my PQ node. So I had 5 millisecond traffic loss so far, right? Within 150 millisecond, R1 reconverged. So as soon as R1 converges to a new path, I have a better path now. I'll stop using FRR. I no longer need to use FRR. From look at it from R1's perspective. R1 had to use FRR because it didn't have a path. But now R1 converged. It has a path now. Stop using FRR. It will send traffic to R2 with just single label, 16,006. It doesn't need to use the FRR label stack, right? But has R2 converged at that time? R1 converged within 150 millisecond, and say at 150 millisecond, R1 generated the LSA to send it to R2. R1 has to generate the LSA or LSP update, right? That packet, it has to reach R2, R2 has to receive it, R2 has to process it, then generate an update for R3 or flood that update to R3. Say R2 takes another 150 milliseconds to do that.
But here it's a PQ node, right? It's a targeted LDP session, right? So
no, there's no, yeah. So that's what's right. It will continue to use PQ as long as it has not converged. R1 will continue to use PQ as long as R1 has not converged to a new best path.
At T0, the primary path is programmed.
Correct.
Now, as soon as the backup path is already programmed in itself,
correct.
My the immediate backup path is to reach R4.
Correct. But that's a backup path only, remember. Correct. That's not my best path.
As of now, when the primary path goes, there is no other path.
There's no other path, and that is.
We have to take the backup path, which is already programmed.
Correct.
So R4. So the packet comes to R2. R2 knows how to send the packet. No need of any convergence for R2 side.
R2 side, no, let's look at only from
have
R1.
any convergence. So
Forget about
I
R1.
can send it.
It will send it.
So there is only that 5 milliseconds for the R1. Only that traffic drop is currently seen.
Correct.
So far my understanding is right?
Correct.
So why R2 has to converge at this time?
No. Forget about R2. So R1 doesn't have a best path right now. It is using an FRR path.
Yeah.
It doesn't have a best path yet.
So can I consider the backup path or the best path,
So
right?
we are considering, but for R1, so there is a FRR flag set actually. There is a flag. As long as the flag is set on that path, it knows that it is a FRR path only. It is still not my best path. I have not reconverged to a new best path.
So this will be, even though I get a, in this topology there is no best path, right?
R1 doesn't yet have a best path. So see, if R1 recalculates SPF, R2 will be its new best path, right? Or its only path now, but R2 will be its new best path after converging. So forget that you had LFA at all. In the normal case, what happens, R1, when the link goes down, R2 has to rerun SPF to figure out new path. That's what R1 has done. So because you have FRR doesn't mean R1 will stop running SPF again to figure out a new best path. That doesn't stop. It's a normal IGP wave, right? So R1 would have taken, say, 150 milliseconds to converge and figure out that R2 is my best path. As soon as it figures that, right, it will stop using FRR. Because I have a new primary path. I didn't have a primary path, so I used FRR. Now I have my primary path again. Stop using FRR. Continue on my primary path, right? And that takes 150 milliseconds, assume in this case. That point is clear now, right? Yeah. Okay. So now, at 150 millisecond, R1 has converged. Has R2 converged? No, because R2, first of all, there's a R1 say generated the update at 150 milliseconds. After it has converged, it will generate a link state update or a link state packet, whatever, and it will send to R2. So by the time R2 received an update, already 150 milliseconds has passed from t is equal to 0. R2 will take another 150 milliseconds for it to run its SPF and then figure out that R3 is my best path, right? So which means that t is equal to 300 milliseconds, R2 has converged. But at t is equal to 150 milliseconds onwards, R1 has started sending traffic to R2 on the normal path. It's not using FRR anymore. So which means R2 will drop traffic for that 150 milliseconds. From t is equal to 150 milliseconds to t is equal to 300 milliseconds, R2 is dropping traffic.
Will it drop or will it send it back to R1?
Oh, it will loop it back. Sorry. Yeah, I mean the point is it will loop it back and TTL expiry. You see show controller stats, TNX, you see TTL 0, that count incrementing a lot during that time. That's the way we check if a micro loop has happened or not. Check for TTL 0 packets, are they incrementing suddenly, right? But in this case, yeah, R2 will loop it back, R1 will loop it back to R2, the loop goes on till TTL expires. You're right. But the point is traffic has dropped. So t is equal to 150 millisecond to t is equal to 300 millisecond, traffic has dropped. So how much traffic drop have I experienced so far? Cumulative?
300.
No.
155.
155.
Okay, 155.
155. So far so good, right? This calculation is fine so far on WebEx as well. Okay. Yeah. Anyway, interrupt me, whatever. So at t is equal to 300 millisecond, I have already experienced 155 millisecond of drop, right? Now look at R3's perspective. R3 is not my PQ node, right? Say at t is equal to 300 millisecond, R2 will generate update, give it to R3. R3 takes another 150 millisecond to figure out that run SPF, figure out R4 is my new best path. T is equal to 450 millisecond. Alright. So for how long have I dropped traffic now? 305 millisecond drop. Post that, if R3 can somehow send traffic to R4, R4's best path it will take. So you don't have a drop post that. But I have dropped traffic for 305 milliseconds. So total traffic loss is not 450, it's 305, I'll correct it. Alright? This is 305, not 450.
It just on basic development. So so now my primary path is done, right? I'm taking the backup.
Initially.
But even though my primary path is not converged at all, it's completely down. So my backup path will be my best path.
Yeah,
then flag will get removed, right?
No, flag will remove once R1 calculates its new best path.
So this is the same.
Yeah, same thing. So R2 and R3 anyway, they are not part of TILFA. R2, R3 are pure IGP convergence. But coming to R1 as soon as link went down, cut over to the FRR path. But it's an FRR path only. It will continue to use FRR path till it has a new normal best path. which in this case turns out to be R2 only, but my label stack is different. FRR label stack is 2 labels, but my normal best path label will be only 1 because my best path is that now, right?
No, will it switch to the 2 label path to 1 label path?
Yeah, it will. After once R1 converges, R1 will not use 2 labels anymore. It's not using the FRR
That
path.
is after that 150
Milliseconds. Once R1 converges.
This is how it works.
Yeah. This is micro loops. So from t equal to 300 millisecond to 450 millisecond, R3 will keep looping it back to R2. But R2 will send it back to R3 because R2 has converged by then. Alright? At t is equal to 450 millisecond, the entire network has converged now, or whatever, and the path is converged. So you have a 305 millisecond drop so far. This is not acceptable, right? You need a sub 50 millisecond convergence, but in this case, you converged very quickly, within 5 milliseconds, but your neighbors, till you reach the PQ, have not converged. This is normal IGP propagation delay and SPF delay, blah, 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 right? So this is not acceptable. So this is where micro loop avoidance comes in. So what you do is, on R1, you pre-calculate a time. As a network designer, you need to know that for how much time probably my network will take to reconverge till the PQ node. I have kept it as 2 seconds. Assume. I know that in this case 450 milliseconds is good enough, but I have kept it as 2 seconds to, just in case it takes more or whatever. So till, again, RIB update delay. This is the RIB update delay. So once I have an FRR path and my convergence, I reconverge to a new best path, which means I'm updating my RIB. That's when I get my new best path, right? When the RIB is updated. Correct? So I'm saying don't update RIB till 2 seconds. So if I don't update RIB till 2 seconds, I continue using my FRR path. Because I don't have a new best path. Right? Within that 2 seconds, my network has converged, I don't see a drop. So after 2 seconds, I'll stop using FRR path and use a normal path, send traffic to R2. R2 has already converged by then, it will send to R3. R3 has already converged by then, send to R4, traffic goes. So the config for that is micro loop avoidance segment routing, micro loop avoidance, give a RIB update delay.
What is the default?
You are sending the update, but you are not updating that in RIB.
Yeah, so SPS calculation has done within by 150 millisecond. SPF has calculated that my best path is available, but it cannot update RIB till 2 seconds. And within that time, rest of my network has converged. So I don't see a loop.
What will be the default value?
There's no, you have to configure it. There's no default value. If you just give micro loop avoidance, then it doesn't know when to cut over to the best path, right?
So if I am not having this configuration, and even if
I don't think it will work.
And even if I am having segment routing configured, then also I will not see less than 50 millisecond.
No, because then my neighbors have not converged, right? I have to somehow delay cutting over to my best path, I mean moving from FRR to my best path till my network has converged. That's what I have to do. Continue using FRR path till my network has converged. I have to ensure that, right? How do I ensure that? Unless I give a RIB update delay, it's not going to happen. Got it, right?
Krishna, does this happen per
Yes.
Does this happen per prefix
Yeah,
or
per prefix. Per prefix.
this per? Okay.
So if your TILFA is per prefix, then this also will be on a per prefix basis only.
Okay. Okay.
LFA configured on every box. Not getting how we will manage it.
Okay.
You have LFA configured on R2, R3, everywhere, right?
R2, R3, but who's doing the cutover? So you have LSA configured, you have micro loop avoidance all configured, but all that comes into place for the person who's doing the cutover from FRR to my best path, right? Who's that? It's only R1. So you can have it on R2, but R2 is not doing the cutover. Or whatever, reopt in this case. R1 is reopting. Reoptimizing, I'm sorry. That is micro loop avoidance. After 2 seconds, my traffic goes fine without FRR. Right? That's it.
And then recovery, same path, right? When the primary link.
When the primary comes back up, say it takes 150 milliseconds for it to converge. In that case, it's not cutting over from FRR. It was on a best path, it suddenly has a new best path. Then it's immediate because there's no chance of a drop in the network.
Again, R1 has to plug to R2 and R2.
Correct, all that has to happen, but will traffic drop happen?
Okay, already R1 is sending to R6.
R1 is sending to R6.
Only convergence takes time, but the traffic is forwarding.
Traffic is forwarding. So the point is, in case of best path to a better best path, you don't need to delay it at all because your traffic is not going to drop. Only in case of FRR to a new best path, if path is the same, then traffic will drop because my downstream neighbor is not converged yet. Got it, right? Yes, I guess this is the session. If any questions, let me know. Yeah.
This microloops happen in all the types.
All networks. In fact, when we do convergence testing, right, we have to enable this. Otherwise, convergence will be bad. We have to enable this, ensure that we are waiting. I mean, we have the repub date delay configured to correct value. Generally, I configure a high repub date delay. I mean, because I'm just testing locally. Maybe in real networks they won't do that. I configure 3 seconds because I know in 3 seconds, no matter what, my network would have converged. Here I gave 2 seconds just for an example. In real life, they may not give 3 seconds or 2 seconds.
Even without FRR, I don't have any FRR, I'm not protecting it. Even that time, we can.
You have micro loops.
We have to give it, right?
No, if you are not using FRR, I mean, if you don't have a FRR path, then having micro loop avoidance is not going to work at all. Because you need FRR path.
Anyway,
You always think that it's going to be second.
Your traffic will be dropped.
exactly.
Because you don't have FRR path at all.
So why have we gone with non-default option? I mean, could we not have gone with the default option also there with say 1 second, 2 seconds? Is there a
We could have, it's very network dependent.
Even with TLS.
I think it's very network dependent. If you have a 5 router topology, it will be very fast. You have a 100 router topology, it will be much slower. It depends, right? Or maybe enhancement that ISIS or OSPF knows that I have 100 networks, maybe I should have a default value of 10 seconds. It's too high. But you run into all that. It's a network designer's job. You can only hardcode default values when you know that whatever be the network, this is not going to change. Then you hardcode a default value. But when it's very network dependent or topo dependent, right, you cannot really give a default. Maybe that's the reason they haven't given a default.
So we are, while doing testing, we are seeing that, okay, we are seeing loss of 500 milliseconds or something
We do
like that, and accordingly we will set the repub date delay time.
I put it at 3 seconds. I mean, like,
But let's say that.
But you can do that.
How for the network admin, how will he get?
He has to figure out that, again, right, convergence is a function of the CPU. CPU, right? Now, how busy is my CPU? My CPU is at 5% load, I get it, I do it within 50 milliseconds. My CPU is already at 80% doing some other task, and I get this I have to do convergence now. It may not be done in 15 milliseconds, I may end up taking 300 milliseconds. It's dependent on the load and a lot of factors.
So even if you are setting the value, let's say 1 second, 2 seconds, you never know, somewhere in the future even that value may not
be sufficient. So in that, generally you do whatever may be your worst case, load CPU to 90%, see how much it's converging on that node. Then you take the worst thing multiplied by 1.5 or 2.
to take help of automation and all those.
Automation, I mean, again,
keep on pulling the data and.
Pulling the data, correct. Do a lot of testing basically to see how much time it's taking to converge at 80% load. Multiply that by 1.5 into number of nodes. Again, this node can be a very powerful node, the downstream node may not be so powerful, it may end up taking even more time. It's a design choice. It's basically a design problem at this stage. Yeah. So, any questions on WebEx so far?
Do you have any other example of, while doing your testing, do you have any other example of micro loop avoidance other than this, that how did you
so we generally have ring, I mean I'm testing a UMMT type of solution, which is like I have like 2 rings or 3 rings connected. So even if you have a whether it's a ring network or a non-ring network, PQ remains the same, right? So all the routers till my PQ node I don't care about the convergence because it's already on the best path, path to reach. Till the PQ node, how many nodes do I have? How much time will they take to converge? We just have to apply whatever we learned here, right? The same algorithms is applied, that's it. Be it ring, need not be ring, doesn't matter. Star, ring or some weird topology doesn't matter. Apply the same thing, you will get the PQ.
Mostly ring only.
Mostly it's generally ring because RLFA, right, gives very good coverage with ring. For non-ring, RLFA breaks down very quickly because PQ, you don't get a PQ. TRFA doesn't matter. So, but generally we do see, the reason we have rings, right, because you save cost. If you don't have a ring, you end up having a star topology. Actually, you have to, the number of fiber links you have to lay to get a star topology is very high. Cost will be very high. But you connect all of them in a ring, your cost is the least. The least cost way of connecting everything, whether you dig, lay, fiber,
But ring in the sense, I have only one level of backup, right?
Sorry?
It's only one level of backup we can have, right?
Yeah. See, if your PQ node dies at the same time, then you can't help it. You have one level of backup. You have one PQ node.
But in start topology, we have multiple backups.
No, you still end up, so you can have multiple PQ nodes, but you'll end up choosing only one node.
Maybe possible in customer network, instead of having only one backup path, there might be possible that there may be having some 2-3 backup paths.
No, even if they have they can have 2-3 backup
At
paths.
a time they will be choosing one, and if that is also going down,
Then you have to recalculate a backup path. It's not pre-programmed. You don't have multiple levels of backup pre-programmed in hardware. You will have only one level of FRR backup pre-programmed in hardware.
No, but again, once means that R1 to R6 link is going down, it is already having this path.
Correct. One level of
but
FRR has
there
been
is one
programmed.
more path available. Then after the reconvergence happen, that path will become as the backup path, right? And this path
Correct.
will become
Yes, yes. Okay, now that you brought up the point, right? Well, one last thing is difference between RLFA and TILFAs. TILFA will create FRR on the so TILFA, what it will do? Say this link goes down, right? TILFA will calculate what is my, assuming that this link doesn't exist, what is my next best path? TLFA will do FRR on that path. So it's called post-convergence path. If this is down, what is my post-convergence path? This, right? TLFA always programs FRR on my post-convergence path. RLFA doesn't do that. RLFA doesn't look at is it my post-convergence path or not. It will do its nearest PQ. Maybe the nearest PQ is not my post-convergence path. So path can change in case of RLFA once the reconvergence happens. In case of TLFA, path will not change. That's another advantage.
No, I did not.
Okay. I mean, in this network I cannot show it, but the point is, say this link is down. What is my post-convergence path? R1, R2, R3, R4, R5. Assume I had another small ring, and that is not my post-convergence path. TLFA will never use that. TLFA will create FRR only on the post-convergence path. RLFA, that restriction is not. I mean, it doesn't look at that. RLFA can form the PQ node or FRR on the non-post-convergence path, and then once it reconverges, it ends up using a different path.
No, but Krishna, how will you decide that it is a post-convergence path or not? Say, for example, now if you have one more segment between an R6, R1 and R6, how can you say that it is not a post-convergence path or a post-convergence path? How can you define that?
You can see, R1 needs to calculate SPF without the protected link.
Correct.
So R1 will run another SPF without the protected link. It will not consider the protected link as present there. It will calculate what is my post-convergence. It's simple. Got it, right?
No, a little bit confusion still.
Okay. So R1, R6 link is present now, right?
Yes.
And
yes.
SPF is run. Now delete the R1, R6 link. Delete the R1, R6 link. Delete it.
Okay.
The path I have is R1, R2, R3, R4, R5, R6, right?
Correct.
So assuming this link is not there at all, SPF is run, assuming that the link is not there.
Okay.
So that SPF will obviously be my post-convergence path, correct? I mean that SPF
Correct.
path. That's it. That's how you get your post-convergence path.
No, but even in RLFA case also it does the same thing, right? If that link is not there.
RLFA will not look for a post-convergence path. I mean, see, what I'm saying is TILFA will, say if TILFA gets multiple PQ options, it will choose the PQ which is on my post-convergence.
Okay.
RLFA will not look for that. RLFA will directly go for what is my nearest PQ. Whether is it in my post-convergence, not. See, in 99.9% of the cases, it ends up being the post-convergence itself. But in that rare, the whole point is RLFA does not have that consideration in the way it is built. TILFA has that consideration in the way it's built. In that rare chance that my PQ node is not on my post-convergence path, RLFA doesn't care, TILFA cares.
Okay, just one question here. Now you have a small subtend ring between R1 and R6, like R1 connected to R7, R8 and R6. Okay.
Okay.
So in that case, if that link between R1 and R6 is not there, so you can post-convergence can be R1, R7, R8, R6 also, right? So how will that get decided?
No. So R1, R7, R8, R6 is one ring, and then you have this R2, R3, R4 ring, right? Now, remove R1, R6 link and calculate SPF. If R7, R8 is your best path, then TLFA will do FRR on that best path only. But if the best path is not R7, R8, best path ends up becoming R2, R3, okay, then TLFA will ensure that FRR is on that R2, R3 path only. It will choose a PQ node on that path. But RLFA will not do that.
Okay.
But what is the condition where it can be different?
It's a very rare chance. We have to play with metric. But if we play with link metric, we can arrive at a situation like that. We can do that. Just play with link metric. It may take you, I don't know, a few hours to arrive at a topo like that. But you can arrive at it. Because this is a real world case again. I mean, that's the reason they ensure that TLFA will always take the post convergence.
In RLFA, you showed one case where only P space is there and Q is not there.
Not there, correct.
How will it work for the TLFA?
At TLFA, okay, we'll go back. We can go back to. Okay, in this case, you tell me what TLFA should do.
Because here there is no Q.
Fine, that's fine. That's fine. So what is my Q? Okay. R6 is still Q. R6, I have not shown R6 as my Q. R6 is still Q because R6 can directly reach it. Right? So technically Q is there. Q has to be there always. Without Q, traffic will not going to go there at all. The reason I didn't show R6 is
Can use adjacent.
between R5 and R6. Okay. Okay, thanks for attending the session.
Thank you, Krishna. Thanks a lot. So